here, so we should be a little bit less tight. Let's keep coming. Come on. See if we get everybody to fit.
Oh, we're sitting on the other side of the wall. No, we cannot touch.
Yeah, there are specific things we can touch, and we'll get to that in a moment. But this is the main control room at the Savannah reactor plant, and not just the reactor plant, but also the steam plant and the electric plant. So all of it is covered in these panels here, these basically 4 panels. We move from the core itself on the left all the way to the electric plant. So basically, as you go from left to right, you go kind of to higher levels of abstraction from the physics of the core itself. We have what we call a mimic-based system here. So on the walls, you see these geometric shapes that are intended to be somewhat representative of the actual devices that are being controlled. And that was an innovative thing for Savannah that now we still see in modern plants today. But there's a period of time in like the 60s and 70s where not everybody used mimics. And the track record is, for example, that 3 Mile Island was in part a result of operator error that was partially due to the user-hostile layout of the plant, where the whole plant was basically just mazes and fields of buttons and dials without a mimic-based system to make it a little bit more approachable like it is here, especially under duress. So if we start from the left, the leftmost panel over there, that panel deals with the core directly. So all those dials on the wall are showing the insertion depth of the control rods in the core. So the purpose of the control rods is to absorb neutrons. So when you have a nuclear reaction, a chain reaction going on, you have more and more neutrons being emitted as the particles experience fission. When you insert the control rods, they absorb the neutrons and they slow down the rate of reaction by capturing some of those neutrons so that they can't cause subsequent reactions. So we have the dial showing insertion depth in inches, and then little lights on top that would show all the way in or all the way out or somewhere in between, depending on which of those 3 lights is lit. Down on the bottom, it's a little bit hard to see if you're in the back, but on the bottom of that leftmost panel, there are a bunch of switches that turn. And the purpose of those turning switches is the shim control. So as you turn those switches, the rod corresponding, there's one for each rod, and the corresponding rod would go further in or further out. And you'd hold that switch for as long as you wanted it to move. You'd look at the corresponding dial. But in general, the operators didn't have to be shimming all the time, because for the most part, these pressurized water reactors are very user-friendly because they follow the power demand from the plant. So as you ask for more power, the radioactivity comes up. As you ask for less power, the radioactivity comes down. So the shimming of the control rods is really just kind of a trimming action. Or if you know that there's going to be a big demand coming, if you know in about 5 minutes the captain's going to demand all ahead full, you might pull the rod slightly to bring the power level of the plant up just a little bit. But it's not like a moment by moment, oh, I've got to shim and shim and shim. The next panel to the left is the part that I know the least about, so I can try to answer questions, but wouldn't be able to be too much help. It's the makeup feed portion of the plant. So that panel deals with purifying water to provide to the primary loop of the plant and adding the correct chemicals. So just maintaining the absolutely correct water quality. It's full of filters and pumps and monitoring systems, heaters, things of that nature. Then it comes from the edge of that yellow piping area, it jumps across. You can see the yellow makeup feed coming from the left lower edge of the center panel into the plant. So the center panel here is showing the reactor plant as we usually think of it. We have the core in the center, and you can see really readily that this is what we call a once through 2-loop plant. So it's once through because the water circulates through one time. There's not some sort of complex, serpentine path. And it's 2-loop because there's 1 loop on the right and 1 loop on the left. So the water exits from the top, as you can tell by the arrows on the mimics, and it enters from the bottom. Again, you can see the arrows on the mimics pointing into the core. And the path of circulation where the cold water enters from the bottom and the hot water comes out of the top, keeping in mind that the heating element is the nuclear fuel in the center of the core. That's the reason why Savannah could never be approved today, the way that she was designed, because she is incapable of what we call natural convection. If you lost those pumps, you can see there are 4 kind of snail-like shapes, 2 on the right and 2 on the left in red. Those are the circulating pumps, the main circulating pumps. And if those pumps were to go out, she could not naturally convect, whereas modern plants are designed to add the cold water from the top, so it could naturally circulate down. Savannah is a pressurized plant, a pressurized water reactor, and the pressurizer is that kind of pill-shaped thing on the top that's yellow on the top and red on the bottom. So its job is to maintain the pressure in the plant such that the plant stays solid. I believe that pressure is on the order of about 1700 psi, and that prevents the water from boiling. There are different kinds of nuclear plants that are called boiling water reactors, but this is not one of them. So with that pressure, we keep the water in the system from flashing into steam. But on the secondary side, the water is allowed to boil, and those boilers, those steam generators, are those big triangular shapes on the right and the left. So those steam generators that you'll get to see in the containment vessel when you visit it today, they have water that's completely isolated from the reactor core. It's never touching any radioactive material. It does not become radioactive. It just exchanges heat in those boilers. We pull off the steam, which is color-coded yellow, and we run it over towards the right side over here. And this is the secondary steam plant. This is where we use steam to do work. We run it through our propulsion turbines, and then we circulate it back. We circulate the spent steam that's been collected in the main condenser, which is that big blue thing in the center. We collect it with those pumps below the main condenser, and we drive it back into the plant again, and we just circulate and circulate. Not shown there, a small amount of steam is also pulled away from the propulsion turbines to generate electricity. And then that brings us to the final panel over here, which is our electric plant. So these brass-colored mimics show all the So the first of these buttons is the lamp test button. If you look over in the center, there should be a button called lamp test. It's a big silver button with a sign that says lamp test on top of it. Somebody should press that button and look at the lamps. Yeah, hold it down. Yeah.
Hold it down, man.
Seems really convenient, so maybe not. But we still have the term scram. There's a scram button that we can press for that. So please, somebody press that scram button. Yeah. So the plant's shutting down now. The control rods are being slammed into the plant with hydraulic pressure. And if you press the acknowledge button in the center, it'll shut it back down again. Yeah. There you go. So our doctor docents, hardworking docents is very happy to have that with me. During Savannah's career, she was never actually scrammed in a true emergency. Are there any questions?
What are all some of the, there's a lot of plated over parts.
Yeah, I think that those were a product mostly of sort of souvenir hunting when she was first decommissioned.
Okay.
There were more originally, but we pulled back some of the instruments bit by bit and have been able to replace them where they belong. But yeah, there's still some that are absent, unfortunately. A lot of them are probably at Kings Point at the Merchant Marine Academy.
I have to ask why the two engine order telegraphs. That's like a totally different style of the way the board is.
Yeah, that's a good point to bring up. So with a nuclear plant like this, it's the power division between the captain and the chief reactor operator is kind of delicate. They don't want the final control of the plant to be too far away from the plant. So the captain and the chief reactor operator have to sort of operate kind of almost like near peers. Like the captain is just like, just a half step above the chief reactor operator. And so they don't actually command the plant from the bridge. They make requests. So they send a request down with the engine order telegraph. You see the interior needle go to whatever it is they want, this room to respond to. This room moves the handle to say, yes, I've seen it, I acknowledge your order, and I'm executing your order. So that's the purpose of the engine order telegraph. Also, we have those two joysticks that you can see on that panel very near the telegraph. So that's another innovation about Savannah. So Savannah was basically fly-by-wire. She had these little electric actuators for the main head and the stern throttle valves, whereas most ships of her time would have these big kind of ship's wheels to operate the valves. And she does actually have those as well in the back of the engine room. But on a day-to-day basis, you just use little joysticks. Very luxurious.
So is there an actuator on the valve?
Original colors, the only difference is that back in the day, there was insulating lagging over all the piping. And that lagging had to be removed because it was asbestos, high-tech material that everybody wanted, miracle material. We had to take it off, of course, and the pipes were repainted to the original colors that the asbestos had been painted at the time. So, working off this color coding, there was a question in the control room about what happens for propulsion if you lose the plant. What happens is your diesel generators kick in, they do supply electric power to the plant, and that electric power is driven to this induction motor. So this is a take-home motor. I always forget exactly what the horsepower is. I think it's 750 horsepower, and it will clutch in to the main reduction gear. And this big motor is able to give you about maybe 3 or so knots on a good day, just enough to keep the bow of the ship pointed into the weather and maintain hydrodynamic stability of the hull. It clutches directly with a small...
Attention guests, in 10 minutes, we will be beginning our National Maritime Day ceremony. The ceremony will take place on the promenade. You can reach the promenade deck from the main stair tower, center of the vessel. Please join us in 10 minutes for our National Maritime Day ceremony. Thank you.
We'll probably make it back up to the purser's desk in 10 to 15 minutes, so you guys will be welcome to join. But yeah, just to continue, so yeah, this interfaces with the main bolt gear with a small pinion gear. You would have seen the main bolt gear out on the deck or out on the pier when you came in. It was kind of cut into sort of a pie wedge shape. And it was there because when Savannah was decommissioned, there was a ship with not a similar ship, but a similar propulsion system with a similar reduction gear set, which goes to show how once you come from the control room into this room, from out here, we don't really care where the steam comes from. This is a conventional steam propulsion plant. It's not inherently nuclear in nature. The steam just comes from somewhere, whether it's an oil-fired boiler or whether it's a nuclear plant, doesn't particularly matter. We pull the steam in here, and we run it through our propulsion turbines and through a reduction gear set. So this other ship needed another reduction gear, it needed a bowl gear. So they actually cut a hole in the side of this ship, which by that time had been decommissioned, pulled all the machinery out behind us, and then winched out the gear with the chain falls and gave it to this other ship and put everything back again, which speaks to the care that Marriott was taking of this ship, because they could have just left it, barely patched, but instead they put everything back in as best they could, although there are some piping flanges that are still unbolted. And also the main turbine generators that we talked about that pull a small thread of the steam from the core. Most of the steam goes to the propulsion turbines, but some goes to the main turbine generators. They're located over there. They're that kind of off-white color. So they're the main way you generate electric power for the plant. The diesel generators are on the engine room lower level on this side, kind of under my feet. And the seafoam green stuff behind me is the ship's air conditioning plant and distillation plant. The yellow, as I mentioned, is the reduction gear set. So our turbines here operate at about 5,000 RPM or so. And we need our propulsion shaft, which runs straight under your feet in the center of the room. We're standing very near the center line of the ship here, and we can tell what the center line is by looking for that propulsion shaft. The propulsion shaft needs to turn at fewer than 100 RPM. So we have to bridge that gap somewhere between 5,000 RPM and 100 RPM. And we do that with these reduction gears. So we spin these pinions coming out of the turbines really fast. They interface with the first stage of our double reduction gears. They interface with another set of pinions, and those pinions finally drive that big bowl gear. And when you look down through the grate there at the propulsion shaft, what you see is the shaft itself and also the main thrust bearing, which is the point at which all of the propulsion power of the ship interfaces with the ship's hull. So it basically provides a pushing point for the turbines and a pushing point for the screw against the ocean.
Where do you change the direction of the rotation?
So what you do is there's an astern stage to the low pressure turbine over here, And what you would do is you would close your head throttle valves and open your stern throttle valves, which is something you can actually do simultaneously if you want to. There's a maneuver called a crashback, where you are simultaneously closing your head while you're opening your stern, like at the same time. And that is the largest transient that you can possibly inflict on a ship's propulsion system. But so you start driving steam into the astern stage instead of the head stage, and it will reverse the direction that the pinion turns. So in such a case, we'd only be getting propulsive power out of that pinion over there. And on this side, we'd be freewheeling. But the turbine blades would not be causing too much windage because there's a light vacuum drawn inside of the turbines in a case like that when you're not actually feeding steam.
How many propellers does the ship have? Just one?
Just one.
Oh, just one.
Yeah, just one shaft that runs down the center line of the shaft that goes to the one propeller.
How long is the shaft alley? It's like.
That's a good question. I'm not sure. It may be in your guidebook,
Okay.
but I don't know offhand.
No,
Sorry.
but we
Yeah.
can always have it.